In this video, I'm going to go over the triangle trigonometry sectors and arc length for the IB Math SL exam. Starting with the basic reminder of what trigonometry is. Evaluating trig functions mentally. There are some trig functions we're expected to be able to do without a calculator, and the faster you can get there, the better. So if you're asked to evaluate something like the sine of, let's say, 2 pi over 3, you're going to want to try to first locate that angle on the coordinate plane. So that's what I mean when I say question 1, what quadrant is it in? So you're trying to figure out the angle 2 pi over 3, remembering pi over 3 is 60 degrees because that's 180 over 3, and 60 degrees doubled would be 120. So you've located yourself on the coordinate plane. You're in the second quadrant. The reference angle would be the angle to get from where you are to the x-axis. So if that's 120 degrees approximately, then the reference angle is going to be this angle here. So to get to the x-axis as fast as you can, so that would be a 60-degree angle in this case, knowing that the x-axis is 180. So we're dealing with a 60-degree angle. Is the trig ratio positive or negative there? So we're asked about sine, and we're in the second quadrant, so we should be thinking positive. And finally, what is the ratio? So knowing that this is a 60-degree angle in here says we can assign root 3 across from the 60, which means 1 would be the other leg, and 2 would be the hypotenuse, so we can answer the sine is going to be a positive root 3 over 2. So we can use triangles to evaluate trig functions in any quadrant if you know your 30, 60, 90 shortcuts and your 45, 45, 90 shortcuts. Some other things we need to know about triangle trigonometry is that you can use Pythagorean theorem and SOHCAHTOA in right triangles only. And then you can use the sine rule and the cosine rule for non-right triangles. And there are some tricks to the sine rule where you sometimes end up with two triangles, and that would be if you were to be given an acute angle and a side across from it, that lets you use the law of sines. But if the other side given is something bigger than the one across from your acute angle, then the first thing you're able to find, which is the angle here opposite the 15, could be acute or it could be obtuse. And you'll have to check for both possible triangles in a situation like that. Other times, like if that 15 had been a 10, for example, we know that there's only one possible triangle because the angle across from the 10 would have to be smaller than 40 in that case. So usually there's only one possible triangle, but there are cases where there are two possible triangles. And in cosine rule, that's not going to come up as long as you use the cosine rule twice to solve a triangle, rather than using cosine rule followed by a sine rule. We also need to know that the area of a triangle can be found using 1/2 AB sine C. This is in the formula booklet, but you must know that if you have a triangle with a 10, 12, 40, and a 60 or something like that, when you use this formula, A and B can be any two sides, like in this case the 10 and the 12, but C must be the angle that's included between the two sides. You cannot use 10 and 12 and the 60-degree angle in this triangle in order to find the area. It must be the included angle. So let's do some examples together. This is question 1 off of an exam, so the easiest question on the exam, and it's a calculator test. So the first thing we're asked to find is AC, which is this length over here. You can call it little b because it's opposite angle big B. That's a convention that we like to use. And it helps you when you're setting up the law of sines to think about an angle and its opposite side. So if you have an angle and the side that is opposite it, you should be using the law of sines. You can set that up as the side over the sine of the angle, or the sine of the angle over the side. You can reverse this fraction, but you cannot do the sine of 10. That would make no sense. You have the side over the sine of an angle. Noticing that our angles are in degrees, so we need to double check that our calculator is in degree mode. Because you're doing a sine of an angle, that's when you need to make sure you're in the correct mode. We have a little b, which is the side we're trying to find, across from the sine of 80. So in this case, we did not need the third angle, though most people's instinct is to try to get the third angle because it's so easy to find. And indeed, we might need it in part B, but in this part, we don't need it. So we're going to cross multiply to solve. Do sine 80 multiplied by 10 divided by the sine of 35, and it equals B. And you'll put this into a calculator and find out that B is, I don't have my calculator handy, but I think it's 17.2, and we'll put units on it. And that's the side length AC. And then find the area of triangle ABC. So this is where we're going to use our 1/2 AB sine C formula, not 1/2 base times height. That only works in right triangles, and we don't have, or Right triangles or where you're given the height, but it has to make a right angle with the base. We don't have that here. So we can use any two sides. We have two sides now. We have the 10 that was given, and we have the 17.2 that we just found. But if we're going to use those two sides, then we must be using this angle here, which is 65 degrees. So you're going to have to use area equals 1/2 10 times 17.2 times the sine of 65. And I'm not, again, not totally certain that that 17.2 is correct, but your calculator can verify what it is. And then you could use your calculator to evaluate the rest of this as well. In the interest of time, I won't finish that example. So here's another example. This time it's telling us that we have two possible triangles with the given information. So this is one of those special cases where the first angle you find could be acute or it could be obtuse. So if I just labeled a picture with the given information, I have HK is 18 in both cases, same length. JK is 15 in both cases. So you can see what's different is that angle J. Angle JHK is 53, and that's the same in both triangles. So you can see that they fixed those lengths, fixed that angle, and still J can be different. It just depends on whether that the side labeled 15, is it bending out from J or is it bending in from J? So I could have an acute angle or an obtuse angle based on the same givens. It's asking us first to calculate the size of angle HJK, that would be the angle at J, in triangle 2. So the setup is going to be the same no matter which triangle you're in. It's going to be 15 over the sine of 53 and 18 over the sine of J. And then you will be cross-multiplying to solve. And we have to remember to use an inverse when we're solving for an angle. So that's going to be the last step we do. So J times sine of J times 15, 18 times the sine of 53, and then divide both sides by 15. I like to do as much as I can without the calculator first, and then I'll go to the calculator, and I'll do the inverse sine of this answer. And what it's going to give us is an acute angle. It's going to give us, because when we do inverse sine on a calculator, it always gives us an acute angle. So it's going to give us this angle, but it's asking us to find the one in the second triangle. So if J, let's pretend, because I'm not going to switch over to the calculator screen, so let's pretend it comes out to maybe 70 degrees or something like that. Then you need to make sure you can subtract from 180 and find the second quadrant answer that has the same sign. That would be 110. So you want to be giving the quadrant 2 answer, or the obtuse answer, of that same angle. So just remember, so I can show you what I'm talking about here. Remember how when you do inverse sine of a positive, it's giving you a quadrant 1 answer. It's always going to give you an acute answer, your calculator. But there's another angle in this quadrant that would have the same ratio of opposite to hypotenuse, and so you'll have to subtract from 180 in order to find that. In that case, it would be 110. And then calculate the area of triangle 1. So in this case, you're going to want to use 1/2 AB sine C using the two given sides, but you'll need to use angle K, so you'll have to subtract whatever value you get from J and 53 from 180. Find K and use that to calculate the area. This is a non-calculator question. The following diagram, and this is also a question 1, so an easy one from an exam. And the following diagram shows us a right angle triangle, and the sine of A is given as 5/13. That's information you can put right on the diagram. Now, we don't actually know that this length is 5, and notice I'm doing opposite over hypotenuse. We don't know that the length is 5 or that the hypotenuse is 13, but we know that whatever they were reduces to 5/13. So the ratio is going to be 5/13. And it says show that the cosine of A is 12/13. So cosine is just adjacent over hypotenuse. So we somehow have to show that this side comes out to 12. We can show that using Pythagorean theorem because we know that 5, 12, 13 is a Pythagorean triple. You can either show it this way, that the left side comes out to the right side, or you can solve for it yourself using something like 5 squared plus b squared equals c squared, 13 squared, and therefore b squared equals 144 and b equals 12. And once you know b is 12, then cosine would be 12/13. And then find the cosine of 2a. So this is a rule of thumb for anywhere on our exam. If you see a double angle like that, cosine 2a or 2 theta, or sine 2a or sine 2 theta, you're not supposed to be multiplying anything by 2. should be going to your formula booklet and finding an identity that you can use as a substitution. So there are a few identities for cosine double angle, so that you can replace cosine double angle with something else that you can evaluate, because we don't actually know the angles in this triangle, nor are we asked to find them, nor would we be able to find them without a calculator. So we're going to be doing them using the identities instead. Pardon me while I pause. Okay, I was just looking up the best identity to use there. So like I said, there are 3 for the cosine double angle. The one we can use might be the most straightforward is the first one given in the book, which is that it equals cosine squared minus sine squared. In this case, instead of theta, we can call it a. And we have the cosine and we have the sine, and they're easy enough to square. And so that's how we can get away with doing cosine double angle without actually knowing what the angle is. So if I have the cosine of a squared, and remember that that's what a squared means when it's inside a cosine function or a sine function like that. It means the quantity squared. So I have the cosine of a. I know that that's 12 over 13. That was given. And I have the sine of a, which is 5 over 13, and that was also given. This is a question where it's possible to get part B without ever getting part A. And then we can simply evaluate to figure out what the cosine of 2a would be. So I have 144 over 169 minus 25 over 169. And then we can subtract 144 minus 25, be 119 over 169. And that's it for this one. And then see if we have some more complicated examples to go over. Oh, we have to go over the second half of the video, which was arc length and area of a sector. So these are in circles. There's 2 really easy formulas. They're both in the booklet, but it's extremely important that you know theta must be in radians when you use these formulas. What that's going to look like is if you have a circle, let's say radius is 10, and this angle was 50 degrees. If you're trying to find the length, let's switch colors here, the length of the arc for that 50-degree central angle, you can use the formula L equals r theta. But if you use r as 10 and theta as 50, the answer you get isn't going to make much sense. So if you do 10 times 50, and by the way, this is not the correct way to do it, that would equal 500, which couldn't possibly be the length of that blue line if the radius is only 10. So, and by blue line, I meant blue arc, right? It's curved, but it is a linear distance. And 500 doesn't make sense for a radius of 10. It's far too big. But if you were to convert 50 to radians first, and the radian conversion is going to be to multiply by pi over 180, that is going to come out to a value more like maybe on the scale of 18 or something like that. And that's a much more reasonable length for that arc. So you want to make sure that your angle's in radians if you're going to use these formulas. And here's an exam question to illustrate it. We have an angle that is given in radians. There's no pi in there because it's already been worked in. If you can remember, pi is approximately 3.14. That's what half a circle would be. Then you can see why 0.7 makes sense as a radian measure for that small angle there. It's asking us to find the length of arc ABC, so that's really straightforward. L equals r theta, which equals 5 times 0.7. You can evaluate that on a calculator. Find the perimeter. Sorry, just got a little messy there. Find the perimeter of the shaded sector. So the perimeter is going to involve the arc as well as 2 radii. So we're going to take our answer from 5 times 0.7 and add 5 and add 5. That's a trick. They love to ask this question. That perimeter would involve the addition of 2 radii as well. And then the area of the shaded sector, it's a nice straightforward question. That's why it's question 1, would be 1/2 r squared theta. So here we could just plug in the r as 5 and theta as 0.7, and again, evaluate with a calculator. That's all for this video.